Hello. This is going to be an introduction to inferential statistics, working with one variable specifically, but we're going to be looking at the bigger picture, the concepts, four fundamental concepts as we call them of statistics. We'll start off with a little bit of an intro to thinking about what it means to know something. So the general definition, or sometimes accepted, it's discussed and debated and so on in philosophical circles, is that knowledge is justified true belief. So it has to be a belief. I believe something to be true. And this is kind of important these days. So we're doing this in February 2021, where we know we have a lot of conspiracy theories going around, whether it's about COVID, whether it's about QAnon stuff, about weird lizard creatures or whatever it is. So if you believe something to be true, that's part of knowing it to be true. But then you need to justify that belief, and then that belief has to actually be true. This is sometimes the most difficult thing to do. So I'm not only asking you to think about things like QAnon or other conspiracy theories out there and kind of laugh and smirk, but also think about your own things that you know, and to what extent you can really justify those beliefs and make sure that they are true. So how do we do it? We do it with evidence. So evidence can come from authority. So authority can be either sort of academic or expert advice, but it could also be from power. So authority can be power, or it could be trust, I guess, is another way. Revelation or imagination is another way that humans have traditionally known things to be true, and sometimes that works well and sometimes that does not. So experience. We have experiences, and from those experiences we learn things to be true. Then we're getting a little bit more and more distant from just accepting things and going towards more kind of questioning the beliefs that we hold, and finding more rigorous, or I guess, for lack of a better word, scientific. So systematic observation is another. So trial and error. So you try something, didn't work, try it again, try it a different way, that way it worked. So now I've learned something. So that goes for more practical things like knowing how to fry an egg, or knowing how to boil an egg, or knowing how to bake bread. So sometimes trial and error, as we've learned in our household where we have a sourdough starter going. Formal reasoning. So that's getting more into the realm of philosophical. So we have inductive and deductive reasoning, which I'm not going to get into in depth in this presentation. We also have non-inferential versus inferential. This bracket doesn't need to be there. So things like we've dealt with non-inferential statistical reasoning, and we're going to be introducing ourselves. I'll be introducing you to inferential in this. So research as formal reasoning. Inferences must be justified. So remember, it has to be true and has to be justifiable. So we've looked at non-inferential statistics. We haven't really talked about practical significance. We will talk about that when we look at two variable scenarios. But we've looked at, is this a big difference? Is this a big number? We looked at variation. We've looked at center. We've looked at shape in measurement variables. And we've looked at percentages or frequencies in categorical variables. With inferential statistics, we're going to be focusing on in this course is confidence intervals as an inferential statistic, and you'll see that at play in the next few weeks. Symbols you'll need to know by heart. So this is a sample mean. You got to learn this by heart. This is a population mean. Sample standard deviation, population standard deviation. So that's a mu, Greek letter mu, and a Greek letter sigma. Four fundamental concepts of statistics. this is where we're going to introduce them. I got this, I'm following, or again, going back to basing, how do we base our knowledge? I'm not just making this up. I'm getting this from a respected scholar, Sally Caldwell, from her statistics textbook. So, census versus sample. We rarely are able to get all the data because census are quite expensive. We're going to be probably having one coming up in Canada soon. So the Canadian government can afford to do it because all of us chip in collectively to do that. What does the mean now? Let's say we wanted to find out what the mean number of hours of sleep of George Brown students is. And that would be kind of a challenging task to get every single student. By the time we got every single student to respond, we'd probably be into the next semester, and then we'd have a whole new slate of students. So we can't ask every student. So what we're going to do is we're going to just ask, what is the mean number of hours of sleep of George Brown students? Well, we can't ask every student, so let's just ask about 200 students. So it's taking a sample. And we're going to make an inference. So we're going to make a prediction. We're going to make a guess of what the population mean will be based on what we found in that group of 200. Now, problem is with making inferences, we don't know if that sample is a good one. So we can grab 200 people who just are chronic sleepers or chronic non-sleepers. We don't know, chronic insomniacs. So inferential stats helps us make inferences, and we're going to do that by adding, subtracting a bit of buffer. So those 200 may not be a good representation. We know there's going to be some error. So we're going to be adding and subtracting a little bit on top, a little bit on the bottom to account for that. And that's where those confidence intervals come from. First concept, random sampling. In order to make a valid inference, you have to start from a sample that is conducted randomly. We'll talk a little bit about what that means, but I know that all of you who took the Math 11-12 course struggled with that concept of a random distribution. Remember in the contingency tables. So thinking about randomness is not easy, and conducting a random sample is not easy either. So don't take this casually. To take a sample randomly means the following three things. You can see them. Every member of the population has an equal chance of being chosen. Each individual is chosen independently, and all combinations, even the weirdest ones, are possible. So every person has an equal chance of being chosen. So if I'm taking 200 students from all George Brown students, then I can't just do something like take people with the letter A, whose first names start with the letter A. Because then not everybody has an equal chance of being chosen. I can't go to the cafeteria because maybe not everybody goes to the cafeteria, and I can't go to the gym, assuming school is open and so on, because not everybody goes to the gym. Each individual chosen independently, so that means that when I choose one person, I don't say, hey, do you have some friends that I could also do a survey on? Because that way those friends are not chosen independently. 3 combinations, all combinations, even the weirdest ones are possible. So just because you take a random sample of 200 and it turns out that they're all plumbing students, you're like, yeah, that's weird. But since I did it randomly, if that's what you did, then that's possible to get a weird sample, and it's not valid then. So sampling error. Every sample you take, every time you take a group of people out of a population, you take 200 students out of all the George Brown students, you take 200 or 1,000 Canadians out of all Canadians, there's going to be error. So if I calculate the average number of hours of sleep from that sample, from the population, there's going to be error. Most sample means, remember sample mean is, sorry, let me just get the pen back. Most sample means, right, this is the X bars, most sample means are going to be close to the true population mean, but a bunch of them are going to be off. Very few will be perfectly bang on. This error is called sampling error, error due to sampling. because of it, we cannot make automatic inferences. So you can't just get the sample mean and say that's what's happening in the population. We have to take into account this error. And remember, I talked about a little bit of a buffer. That's where our buffer is going to come from. So here's an idea for making an inference about the mean, population mean, using sample mean and sample standard deviation. So these terms, or these symbols, are important. Sample standard deviation. So we take the population mean. We're going to try to find out what that is. We're making inference about mu using x bar plus or minus a buffer. And we get that buffer from the standard error, which is basically the sample, comes from the sample standard deviation, as you'll see. Okay, so there's sample standard deviation divided by the sample size. So n is the sample size. So what we're doing is we're formalizing the inferential process here. Okay, so we're taking what people do normally. They see a bunch of people. I see a bunch of young people, and I see that they are listening to music that has a lot of violent imagery in it. And I say, geez, those young people today, they listen to violent music. And then, so that inference may be valid or not valid. And when I do research on it, I can find out to what extent that is true. So that was an informal reasoning that I used, or informal inference. This is a formal inference process. So we want to do better. We can't just take that standard error. So there's going to be a little bit more that we're going to do. So imagine the researcher. This is really, really cool. So the researcher keeps taking samples. So we're back to George Brown. So you take 200. Next week you can take another 200. Or next day you take another 200. And you keep taking 200 every day. A new random sample of 200 students. Okay, so you're never maybe going to get to 20,000, but you'll do it maybe 100 times. So we're going to get a set of sample means that looks like the following. X bar 1, that's the first sample mean. X bar 2 on the second day. X bar 3 on the third day. On the fourth day, on the fifth day, it keeps going. So we get a bunch of sample means. This creates a new data set called the distribution of sample means. We're on to the fourth concept. If the population from which the samples are taken has mean mu, standard deviation sigma, then the distribution of sample means will have mean mu and standard error, sigma over root n. So think about what I just said. If the population, so George Brown students, have a mean sleep of, let's say, 7.2 hours, then the distribution of sample means. What is the distribution of sample means? Remember, it looked like this. X bar 1, X bar 2, X bar 3, X bar 4, and so on. So the distribution of sample means, if you take the mean of all these, it'll be mu. And the standard error, standard deviation, will be sigma over root n. Note as n gets larger, the sample size, the standard error will get smaller. So as n, this is the sample size, at n. So as this gets larger, so let's say it's 1,000. So I was saying 200. Let's say it was 1,000. That means this denominator, because the square root of 1,000 is going to be much larger than the square root of 200. So the denominator gets larger, which means that the rate gets smaller. The distribution of sample means will be normal, even if the original distribution was not. That's important. The standard error is the standard deviation of distribution of sample means. So we mentioned that already. And we can use those two facts to find areas in the distribution of sample means, just like with raw scores. So this is exercise 13, which we're going to do in class on Tuesday. Making inferences with one variable. Again, flowchart. So this is the GBC population. So there's 20,000 of them, right? Here we have 200. And then we take that sample mean here. This is the sample from a population. This is the sample mean. And we're going to build on it to get a confidence interval and make an inference. So that's the inference to population. So in a way, we're taking this and we're telling something, learning about the population from this little bit of information. So that's the idea. Now, in class, we'll do some practice. Thank you for watching.